Hello, my name is Theodora and I'm a PhD student at NUS. Today I'll be presenting our work on scalable quantitative verification for deep neural networks. This is joint work with Jen Leong, Kuldeep, and Pratik. Deep neural networks are used everywhere today, even in safety-critical systems and decision-making processes. And because of their wide deployment, it is increasingly important that these systems have certain desirable properties, such as fairness. We want to ensure that the models we use do not discriminate against a certain population. And privacy. We want to ensure that the models that are trained on sensitive or private information do not leak that information. And robustness. And we want to be able to certify that these properties hold. In this talk, we will focus on robustness. So in the context of robustness, what is the main question prior work has asked? Given a model and an image X correctly classified, are there images close to X that are misclassified? This can be formulated as showing the existence of an input called adversarial example, such that the model misclassifies it. The flip side of this question is proving that there are no such inputs close to X. These are the two main questions studied. Consequently, there has been a long line of work that developed techniques to answer these questions, from attack heuristics to testing methodologies and verification techniques. But in machine learning systems, we are often interested in properties of distributions instead of a single input that satisfies a given property. For instance, for robustness, the distributional property is asking if I sample inputs from images close to X according to a distribution D, on average, how many samples are misclassified? But is this question relevant to security? Because security often is devoted to finding counterexamples or worst-case analysis. And the reason we are interested in this measure is because it actually forms the basis of the only provable defense we have. This defense works by doing the following. Take a trained model, and instead of running a single prediction for X, sample the perturbations of the given input and pick the most likely class. It can be shown that there exists a provable bound for which there are no adversarial examples. The insight is that within that bound, the majority of images close to X are classified correctly, and thus the model can be shown to be provably robust. Secondly, this is closely related to global robustness, because we are estimating the number of samples correctly classified for X. And robustness is not the only distributional property we're interested in. Distributional properties appear in many queries regarding different fairness criteria. So, as I mentioned, we are trying to ask for how many inputs for how many individuals sampled according to some distribution or population does the model discriminate. Another example is privacy. A well-known empirical measure of privacy leakage is membership inference attack. Say we're given a model that is trained on a population that is linked to some sensitive or private feature. The goal of the membership inference attack is to infer with high confidence that an input belongs to the training set of the model. The attack works by doing the following. It builds a shadow model that is trained with data from the same distribution, and then another attack model helps distinguish between the output distribution of the target model and the shadow model. As a result, we are trying to reason about how often a property is satisfied. That is, we want to be able to establish a quantitative verification framework. So let's look at what we mean by this pictorially. Let us say we're given a threshold that establishes what is an acceptable scenario for how often the property holds. So if the true probability is greater than the threshold plus some error, then we want to be able to return no with user-specified confidence. Otherwise, we want to return yes. And if the true probability is within the error interval, we do not guarantee what the algorithm returns. Our approach to this formulation of quantitative verification is PROVERO, a scalable black box quantitative verification framework. It is scalable in that we showed in our evaluation that we can certify large deep neural networks. We show that PROVERO satisfies the probabilistic guarantees of quantitative verification and returns with user-specified confidence in error. Our technique makes little assumption, such as only the ability to sample from the input space, according to some distribution. So how do we design such a technique? Well, first, we want to satisfy the black box assumption, so we can only take samples. To satisfy the guarantee, we need to take enough samples, though. So how much is enough? Well, we need enough samples to distinguish between the true probability with eta error. So we can use large deviation bounds to calculate the number of samples required to estimate this probability with eta error. Then we can compute the estimated probability from those samples and check whether it is less than the threshold, and if it is, return yes. Now, this estimation approach is generally applicable to all DNNs, but might require a lot of samples if the error is small. So can we do something better? Our main insight is that we can take a few samples first and narrow down where the true probability might be with respect to the threshold. So how do we do that? Well, the true probability can be either on the left side of the threshold or on the right side of the threshold plus the error term. And let's assume we have access to an algorithm that when invoked on these thresholds can return yes and no soundly. What we do is that we start by proving hypothesis on the left side of the threshold. So now if the true probability is less than the new threshold, then we can safely return yes. Similarly, on the right side of the threshold, we create refuting hypothesis such that if the true probability is greater than the threshold, then we can return no. So the insight is that now we reason about how to test with respect to the threshold. We prove that our algorithm is sound and returns with user-specified error and tolerance in the paper. And the main insight is that we can do better when the true probability is further from the threshold. In the interest of time, I will skip these details and move to evaluation. We evaluate PROVERO on benchmarks available from one of the most scalable verifiers, Iran. Iran is an incomplete verifier, so if it returns that there are no adversarial examples, we know that it is sound. However, due to either imprecision or because there are adversarial examples, it can return an inconclusive result. So here the x-axis is the perturbation size, and the y-axis is the percentage of verified instances across a test set. And this is how Iran performs. And we run PROVERO as well, and we find that PROVERO returns a definite yes and no answer with the user-specified confidence, even when Iran begins to be very inconclusive. For example, for a perturbation size of 0.8, the number of verified instances is smaller than 30%, whereas we can still give a probabilistic certificate more than 90% of the time. So PROVERO can be useful in a portfolio solving approach when other verifiers do not return conclusive results. We also show that PROVERO can handle much larger DNNs, such as VGG19 and DenseNet 111. Our second empirical result is regarding adversarial density. In the context of robustness, adversarial density corresponds to a quantitative notion of adversarial examples. So here, adversarial density is when it's larger hump means there are more adversarial samples. So what we can do is that we can use PROVERO to find when the hump transitions from a small hump to a big hump, so that we want to use PROVERO to find the perturbation size for which the adversarial density changes by some margin. So here the blue circle is the perturbation size up to which the adversarial density is within the acceptable threshold. After that, basically the hump becomes too big, so it's above the acceptable threshold. So we find that this perturbation size actually correlates with the perturbation size found by attack-produced adversarial examples. And we use two state-of-the-art attacks to obtain these adversarial examples. So if you want to get a sense of how robust your model is, you don't have to use a battery of attacks, because adversarial density carries over the signal of these attacks. In conclusion, I have presented today our work on quantitative verification, which is PROVERO, a black box quantitative verification framework. And we show that our algorithms are sound. That means that they return with high confidence, as the user has specified, that scale to large deep neural networks. And we also show the empirical evaluation of a new attack agnostic measure of adversarial hardness that strongly correlates with these attacks. With this, I would like to conclude my talk. Thank you for listening, and I'm happy to take questions.
Hi, welcome back live to our Deep Neural Networks Quality Assurance session. This is Gregorio Robles from the Universidad Rey Juan Carlos in Madrid, Spain, and I'm chairing this session. And now we have some time for questions for our third and last paper, which is entitled Scalable Quantitative Verification for Deep Neural Networks. We have Theodora here, who's the main author of that paper. So if you have questions, please put them in the chat. So for instance, Michael has just put one question. So he's asking, how should one define the test space and draw samples from it to do adversarial robustness testing for real-life applications? And then he elaborates, let us imagine a road sign, and a typical problem we may expect is the dirt on the road sign and parts of the sign fading away. Varying pixels at random will probably yield many pictures with the sign itself hardly changed. So it seems lab-measured robustness may be higher than the real-life robustness. So Theodora, any comment on this?
Yeah, thank you, Michael, for the very good question. So that is indeed our work currently does only uniform sampling. So if you were to uniformly sample, you may indeed have a lot of these images which do not depict real world scenarios. So I think this is related to like doing constrained sampling. And our results, our approach basically only requires you that you have independent and IID samples, basically. So you could, there are some theoretical results which only require you to take independent samples. So if you could design a sampling procedure where you sample pixels at random independently. So that means you cannot look at your previous mutation when you do the sampling. Then you could devise a sampler for that specific real life application. In general, it's a hard problem to sample this.
Okay, thank you, Theodora. We move to the next question, and Michael, if you want to follow up, you can put it in the chat. So feel free to do that. So Pidya asks, what would you consider to be the most important next step?
Right. So I guess Michael pointed to a very important direction, which is extending this to other kinds of distributions, like sampling from other kinds of distributions or relaxing the assumptions of the results. Another direction that I'm currently working on is looking at other types of distributional properties where having this kind of statistical guarantees are useful, other kind of security properties, for example, fairness or privacy.
Okay, thank you. Well, there are other questions coming in the chat. I have my own set of questions here just in case. So I come from the tools domain and so on. So I've seen you have, together with your paper, you propose a tool, and I've seen there is a GitHub link there. So the tool, I guess, is open source, isn't it, Theodora? So you put it an open source license. So how is it possible to extend the tool by other researchers? Have you thought of that?
Yeah, so actually the code is not very difficult in the procedure, because what you can actually extend one of the classes and code your own like sampler, or extend to import other kinds of deep neural networks. So in that sense, it is quite straightforward. It's not a large code base. What I think is missing right now from the GitHub is the part of integrating with Clever Hans. So for example, if you want to have other attacks, we have 2 attacks in our paper, but if you want to extend to other attacks, you might have to do some coding to hook together our implementation with the existing implementations of the attack. So I think that would be more difficult.
Okay, and regarding, I mean, I guess the tool now is optimized for robustness as the main property. If I would like to test it and to look for other properties, would that be possible, or is it just focused on robustness?
So no, actually the technique works for any kind of property that is at the moment is defined for a 1-0 kind of distribution, but it could be extended. So what in terms of code changes, you just need to write your own sampler. So basically, when you sample, you need to define what is a 1 and a 0 for a sample, and that can be done quite easily. So for us, we just check the label. But for example, if you want to check a range for example, for like you have a classifier that gives you a prediction over the salary of a person, and you want to check whether that is within some range, you just have to code that up. And if it, as you know, if the range is between this interval, then it's a 1. Otherwise, it's a 0, for example.
Okay, fantastic. So I don't know if any other participant in the room has a question. Please feel free to do it. We still have 4 minutes here, and and it's a pleasure to have Theodora, one of the authors here, answering. So I think you already answered what are the next steps. So and here, so there's another question by Weng Xing. He asks, is there any example that PROVERO failed to provide certificates of robustness? What are the typical characteristics of it?
Yeah, that's a great question. So because I didn't have time to include in my talk. So the way we perform the experiments is that we do have a timeout. So there are cases where either it times out, or it's kind of that ignorance region where we say that the PROVERO doesn't return with any guarantee, so we cannot trust what it returns. So there are some cases, though we have less than, I don't remember the exact numbers, but I think it's less than 5%, something like that, where it returns either none or it times out. The exact numbers are in the paper, but there are instances. And yes, it's quite interesting. The typical characteristic is very hard to determine what are the typical characteristics. But generally, if it's a very, very rare event, it's, for example, you have just 10 raised, like a very small probability that you'll have an adversarial example. Those cases are going to take more samples, so you're either going to time out, or you may have, the threshold is very close to the true probability, so you may require a really large number of samples.
Thank you, Theodora. There's one more question from Yingyue. What he asks is, if you have compared your results with some formal methods to measure model robustness, such as CNN cert.
So I have to check exactly the CNN cert. So we did check. Okay, I'm not sure what CNN cert does. If I'm not wrong, and maybe Jinyu can provide some clarifications. If it's an incomplete approach, I think it's an incomplete approach. So I'm assuming it's an incomplete approach. We did compare with another incomplete approach called Iran, but we didn't extend to other verifiers that measure model robustness. And the reason why we chose Iran is because it's at the time that we wrote the paper, it was one of the most scalable ones in terms of the size of the neural networks that they considered.
Okay, thank you.
Thank you.
So I don't see any further questions, and we are up to 1 minute for the Q&A. So there is still time for a last-minute question. Never better said, it's really last minute, because we have 1 minute. In any case, after this Q&A is finished, you will get a pop-up there in the chat, and you can join the discussion room. And there, Theodora will be in the discussion room, and the discussion room is slightly different than the normal room, because you have video and audio there. So the last-minute question here, it's not a question, it's CNN cert. It's by Jingjue, who makes a clarification that CNN cert is an approach. So Ines makes the last-minute question. Thank you for your presentation. What exactly were the thresholds used in your analysis in terms of LP norms?
So I am guessing you mean the perturbation bounds. So we vary from really small ones, from like 0.01 to 0.3, I think, for MNIST. It depends on also the data set. We can talk more in the discussion.
Yeah, more in the discussion room. See you there soon. So thanks for being in this session. Bye.
Thank you.